I want to make one last observation here. Okay? So when we actually take and roll one dice like this, we get a very simple sample space, and it's just the numbers 1 through 6. 1, 2, 3, 4, 5, 6. And this is our sample space. Okay? Now when we roll 2 dice, it gets a little more complicated because we're rolling 2 and adding the numbers together. Okay? But we found out we can list out the sample space here by making a table. And we have the numbers 1 through 6 here. Right? And the numbers 1 through 6 here. Okay? And so this is one die. Okay, this would be die 1, die 2. Okay, and this would be 2 dice. And we could make this table, so you could roll a 2, 3, 4, 5, 6, 7, 3, 4, 5, 6, 7, 8, 4, 5, 6, 7, 8, 9, 5, 6, 7, 8, 9, 10, 6, 7, 8, 9, 10, 11, 7, 8, 9, 10, 11, and 12. And so this becomes my sample space when I roll 2 dice. And I got all the possible outcomes. Okay? Now, what if I rolled 3 dice? Right? And you could do that. I could get anywhere from a 1, a 1, and a 1, which would be 3. 3 would be the smallest number I could roll. And the largest number I could roll would be a 6, and a 6. 3 sixes. That would be 18. So I could roll 3 dice. I'd get a number between 3 and 18, right? But now, what would the sample space look like? How could I write out the sample space? Now, if you think about this for a minute, what I would need to do is I would need to have another axis with representing that third dice with the numbers 1 through 6. And it would come up off of the page, and it would have 1, 2, 3, 4, 5, 6, like that. And then I could get all my possible rolls. I could get like a 4, a 5, and a 6. And then I would have 15. Or I could get a 2, a 6, and a 3. And I would have 11. So I would have a cube of numbers. Okay? And just like this one here is 6 times 6, and I get 36 outcomes. Right? If I had a cube, it would be 6 times 6 times 6, and I would be finding the volume of the cube. I would find the volume of the cube. So 6 times 6 times 6 times 6 is 216 outcomes. So that means there would be 216 outcomes inside my cube, and they would represent all the possible rolls that I make. Okay? So let's think about this for a minute. Let's think about what's happening with our sample spaces. When I roll 1 dice, this is just a line of 6 numbers. This is a one-dimensional sample space. When I roll 2 dice, I get a square. A square is a 2-dimensional object. This is a 2-dimensional sample space. If I roll 3 dice, I get a cube of outcomes. That would be a 3-dimensional sample space. So now the big question is, if I rolled 4 dice, and you know what? I don't have a 4th dice with me. I just have these 3. But if I rolled a 4th dice, notice I would have a 4-dimensional sample space. Just like we went from 1-dimensional, 2-dimensional to 3-dimensional. Then you would have a 4-dimensional sample space, and there would be no way that you could lay it out anymore on a sheet of paper because you don't have another direction to put that the outcomes for that fourth dice. Here I got 2 directions for 2 dice. I could even move it up off the page in the 3rd direction for the 3rd dice. But now where do I put the axis for the 4th dice? I can't, because it's a 4-dimensional space and we just live in 3 dimensions. This is kind of interesting because you've maybe heard of science fiction stories where they talk about the 4th dimension, and maybe you think that's just kind of strange, maybe a little weird. Like maybe something that math people do, but there's really no reason behind it. Well, we have a real reason for studying the 4th dimension here. Because when you roll 4 dice, that's a 4-dimensional sample space. And to find the probabilities, you have to understand, in this case, the 4th dimension, or what that 4-dimensional sample space is like. And you could roll 5 dice, couldn't you? In fact, in the game Yahtzee, you do roll 5 dice. Guess what? That becomes a 5-dimensional sample space, and so on. So this is one application for higher dimensions in mathematics. Mathematicians study higher dimensions not because they're looking for some strange 4th dimension or some science fiction thing, but because practical applications like this involve higher dimensions in this way. So this is a nice example in order to see that. The other thing to see is that when we draw samples out of a population, oftentimes our samples can have 50. We might draw 50 observations, or 500 observations, or even 1,000 observations. In this case, when I draw, let's say, 1,000 observations out of a population, I'm dealing with a 1,000-dimensional sample space, right? This huge, crazy sample space. And so it's hard to wrap your mind around that. Well, what we're going to do in Chapter 6, we will learn some techniques that will actually make this easy. You don't have to understand all this sort of stuff in order to do it, because there's other theorems and stuff that have been created that help us deal with drawing samples out and how those samples are related to the population. And we're going to see that later on. So